All right, good afternoon. My name is Keita Teranishi from San Diego National Laboratories, California. And this talk is a kind of extension or complement, that complements some years talk on E4S, which is also intended for big software stack. But my talk is just focusing on scientific library software stack, which is supported by ECP project. And I'm just putting my name, but there are lots of developers involved in this project. So as I said, who we are, so we are scientific library developers and making a bunch of libraries and providing lots of capabilities, linear system solver, non-linear system solvers, optimization solvers, and finite element analysis, adaptive mesh refinement, uncertainty quantification, eigenvalue solvers, etc., etc. And so our purpose is, basically our goal is trying to come up with very good software, scientific software ecosystem so that HPC users do not have to bang their head to the monitors just in order to build big applications. And also, we want to also encourage discussions about how to achieve that goal. And again, I can't spend the time to introduce all the people working on XSDK, but as you can see, there are lots of people working on this project, and the PI is Ulrike Meyer-Young from Lawrence Livermore National Laboratory, and I'm in charge of some part of San Diego National Laboratory. But there are currently 21 scientific libraries and a few, 2 or 3 application packages and integrated together and to serve main vehicle of ECP exascale computers. So the role of software scientific source libraries is very crucial to progress computational science and engineering. And because software library basically provides high quality, encapsulated, also documented, and also well-tested, and also multi-use, so can be used in different purposes, and that software, and of course that provides commonly used functionalities of application developers. So, and typically these libraries are well optimized and provide a good set of APIs interface so that different scientific and computational science engineering and researchers actually can use them to build their own applications instead of building homebrew numerical methods just for the sake of their applications. And of course, the advantage is we can, our library is contain complexity, also leverage library developer expertise, which may be one of the major attendees of this conference. And also we are trying to reduce application coding effort, as I mentioned. We still see many application developers spending a great deal of time just to finish their application coding. We don't want to do this. And of course, encouraging sharing code and easy distribution of code. So there's a couple of references for those interested, please access to this website. And so from the user perspective, the use of scientific libraries means, again, reuse. Basically, reuse also customize and extend to exploit application-specific knowledge and also cope with complexity that changes over time. But from a provider's perspective, library developer's perspective, typically scientific library developers are experts in numerical method or maybe high-performance computing research. And of course, they develop software, they try new method or new performance improvement and write papers. But I'm not sure how many people read these papers. Of course, I don't want to disrespect them work, but because it also disrespects me. But most important thing I think more than that, I think the important thing for library developers like us is making much broader impact to the community. But the problem is software itself is not good enough because, of course, libraries provide crucial functionality. Linear system solvers or mesh refinement, etc. But alone is not sufficient. If actually you see many talks in this conference, including one of the preliminary talk of ECP, there are lots of applications using multiple libraries. And however, this is often the case, library developers actually do not consider what is going on outside. But this is not a good idea because we have actually many of them are used in combination. But the problem is how to coordinate them. I mean, they are maybe located in a completely different place or different time zone or maybe different project, funded by different project money. That is so difficult. But we have to coordinate them together so that we can provide better software ecosystem. And the ecosystem, as I mentioned, has been emphasizing a lot in this session, but it is we see the ecosystem as a group of independent but interrelated elements comprising a unified whole. And one of the major, interesting remark was Sir Arthur Stanley Eddington, astrophysicist, and I think he's a philosopher, and he mentioned, so two is actually one and one, but most important thing is what is the meaning of and. And I think our project is actually serve and to improve the ecosystem of scientific software. And this is a diagram of extreme scientific software ecosystem. I mean, this is very, very complicated diagram, but what I want to say about this diagram is on the top. So there are several elements that is required to make good scientific applications. It is not just a quantitative, it is very hard to measure quantitatively, very, very qualitative measurement. And also there are lots of stories associated with that, like a domain component interface, also some software components, and plus testing components, building components, documentation content, etc., etc. And basically, a good application should comprise all of them together. But in the end, what we can do from scientific library perspective is providing domain components, libraries, framework tools, and also applying good software engineering so that we can have a good ecosystem to change vicious cycle to great cycle. But there are lots of difficulties in order to deal with, in order to achieve this. So one of the problems is obtaining, configuring, installing multiple software packages, and need to sustain consistency with compilers, versions options, and third-party packages. We also some software has naming space conflicts, and for one of the examples is very, very generic function name, such as ordering. If one of the library is using a C function written in C, say ordering, maybe other libraries, maybe that is dealing with a sparse matrix or a graph, may have same function name, ordering. What will happen? Of course, this is going to create a naming conflict. We don't want to do this. And of course, also there's a problem with incompatible versioning. Many softwares, many applications only works on specific version of scientific software. And we have to deal with, even in addition to the software dependencies, we have to also deal with versioning to make application work. That is another challenging problem. And anyway, so bottom line is many challenges in order to integrate them, organizing them, coordinating them. So what we can do? Basically, we have to provide a good set of interoperability. So level 1, basically packages can be integrated in the same binary. Very simple, looks simple, but interoperability level 2. Two libraries, multiple libraries can exchange or control data each other. And interoperability number 3, level 3, which is each library can call the other library to perform unique computations. This is actually our ultimate goal, to achieve interoperability of scientific libraries. And there's a little bit history of this project. So one of the reasons we are working on this is previously funded by Oscar project to come up with a geophysics application that requires very complex software dependencies and use of multiple libraries, such as PETC, Trinos, Hyper, SuperLU, and Sundials, and Chombo. And so this is the genesis of the project, and eventually transformed to XSDK project under ECP. Oops, I made it wrong. And our first attempt is coming up with XSDK software policies. This is a crystallization of many of the scientific library developers for the maybe past 20, maybe 30 years. Basically, we just try to create lessons in the small set of the statements to recommend, to also ask or recommend the software developers to come up with, to build a very interoperable software. So we have 16 mandatory policies, and we have 7 recommended policies. And for those who want to join XSDK software collection, we ask to follow all 16 mandatory policies and continue to follow this policy in order to be a member of XSDK. And that project started on 2016. We had only 5 or 4 libraries assembled together. Oops. And now we have 21 libraries in the integrated together, and we are expecting to have more libraries in the next version. And here is the dependency graph of XSDK libraries. And I think Samir already showed the other use cases, other cases of the library, software dependencies. Okay, again, XSDK is required lots of dependencies in order to build them together. So now I want to also talk a little bit about recent activities. So as I said, XSDK provides 16 mandatory policies and 7 recommended policies. But currently, we are asking the individual developers to check by themselves, and there's no formal methodologies to check these policies. So I think this is a very major challenge because, of course, human beings always make a mistake. We need something that actually reduces the kernel possibility of these mistakes. So. And what we are currently doing is we created, again, continuation CI infrastructure. I'm hoping we can also join the way what E4S Forum is working and doing. But in this continuous integration also platform, we are also putting a few policy checker of XSDK. So basically, this is a small set of Python script trying to scan the source code to check some of XSDK mandatory policies. And unfortunately, a few of the policies are very hard to automate. But I think I'm hoping we can find a better way to check that these type of policies using more, maybe more sophisticated, syntactic or language, computer language analysis, or maybe we have to come up with alternatives. And I just want to say a couple of a few examples of how we can check M1, M3, M5 policies. One of the cases is just support, M1, support XSDK community uses GNU-conf or CMake options. In this case, basically we can, with that simple Python script checks the existence of CMake list, configure file, existence of configure file. And also we do interoperability between packages can be testing interoperability packages with inclusion of CMake option, something like that. And also for M3, employee provided MPI communicator. Again, we scan to find MPI COM word in the source code of the libraries because it is prohibited. But sometimes MPI COM word is in the test program or example program. It is totally okay. So in this case, our tester just flag, raise a flag. We found MPI COM word used somewhere, but it may not be illegal. And the last one is M5, provide a documented, reliable way to contact the development team. So I think many of the packages provide websites such as location of GitHub, etc. In this case, basically our script checks the location of website, trying to access that website still exists. And also, we are also trying to actually access the email address of the package owner, but this is really dangerous. So currently we are disabling this because I don't want to send lots of emails to the developer, just by auto-generated email, right? All right. Okay, in the final part of this presentation is the current, recent survey of runtime support of XSDK and also interoperability, and which is available in one of the ECP Confluence repository. And in this survey, we asked all the developers of XSDK and plus a few other scientific library packages funded by ECP, FFTX, Hefty, and Slate. And we started to ask the support of OpenMP. And first question is, do you support OpenMP's multi-threading? So we asked 2 questions. OpenMP allows if you can call up your function from OpenMP threading, or your library is actually calling OpenMP internally in your library. So of course, it seems that are kind of half and half because it really depends on how type of abstraction provided by the library. But once it goes to the question about OpenMP offloading capability, I think this is very important for GPU support in your accelerator support in future. But right now, there are only few people who are trying to attempt to use OpenMP offloading capability. And in fact, in the last week of ECP meeting, there's a session of the early discussing early experience of use experience of OpenMP offloading capabilities, but still there's some lot issues in the performance. I'm hoping that evolution, improvement of OpenMP will reduce the size of the red bar in near future. And we also asked the use of CUDA. Again, I think this is also almost the same. Some library may let user to allow user to use library from inside CUDA or vice versa. And I think because CUDA has been around for a long time, for several years, I think the size of green bar in both cases are kind of high. And once we ask the same thing for HIP, I think only maybe one library is actually officially support HIP, because still HIP is, the status of HIP is infancy. So I think that, I hopefully in the next few years, I think that red bar will shrink to the bottom, and so that we have a much bigger green bar. And I'm also providing SYCL support, which will be used for the programming environment and runtime for Intel's Accelerator platform, and which is part of the Argonne's Aurora supercomputing system. And currently, there are, I think, half of the library developers are seriously thinking about introducing SYCL, and also around more than 30% of the libraries are already started to integrate SYCL. But there's also 16% of the library developers actually not planning to introduce SYCL for certain reasons, for some reasons. And I think one of the maybe reasons is, there's also a programming model project funded by ECP, Cocos and Raja, and these library programming model can actually call either CUDA, HIPS, or SYCL underneath. If they are using this type of libraries, maybe they could say no instead of, even though they are using Cocos with this. In fact, Trinos says actually yes, because it is using Cocos, and internally Cocos calls SYCL. So there must be some, maybe some, so sometimes the data is not indicating what is really going on, maybe rather than some, we have to understand the nuance associated with that. And also we asked some questions about more advanced accelerator support, such as multiple GPU usage. And I'm surprised to see almost 3/4 of the users actually, developers actually enables the use of multiple GPUs. That is good news. And also we also asked if they are planning to use direct accelerator to accelerator communication. And I think 70% of the library developers are thinking seriously, because it will boost performance. And many of the algorithms are suffered by latency and also bandwidth issues of communications. And this is the current status of library interoperability. I would say I'm putting level 3, and blue, basically blue cell means it is yes, and yellow cell means libraries, actually it is supported, but when it is integrated into XSDK, it is disabled. And finally, I want to just show the interoperability of runtime and the programming models. So it is not directly related to XSDK development itself, but it is very important for entire ACP or high-performance computing community to think about the software development to support different type of runtime and the programming model. In fact, many of them actually can coexist. And also few of them needs to serious testing and exploration to see how they work together. But I think this, I think there are a lot of green in cells, which is good news. I mean, maybe it can be very difficult to land them together, coordinate them together to get optimal performance. But at least, multiple applications using different runtime can coexist and can be connected in certain ways so that it can work on big machine. All right, I think I want to also close the talk. So basically, we are trying to make an impact of XSDK software policies and these activities. I think we have been improved code quality and usability of individual libraries from this project. And we are trying to address lots of challenges in interoperability, of sustainability of software developed by diverse groups at different institutions. And also, we came up with a common build of libraries, owing to Spark and also other activities. And I think I think there are last 5 releases of XSDK collection actually established the foundation for the deeper interoperability and performance portability. And we also used this policy to actually create a basis of the software policies, and also that also allows us to engage in wider community users, also other library developers, even runtime and programming model developers, especially over arguing the validity of XSDK software policies. And I just want to finish the talk, and thank you for the listening. There are several useful links for those who are interested. And we have lots of XSDK stickers for those who are interested. Please stop by me or stop by Ulrike and Piotr over there. Thank you.